And this is our last video on our 6.1 class notes on vectors. So we've got one more example that has to do with velocity vectors, but also we're going to use rate times time equals distance and actually end up drawing directed distance line segments. So let's look at this example. A boat is being piloted due east, but there's a current going southwest. Stop right there. What would a boat going due east look like? So a boat going due east, so never eat shredded wheat, so north, east, south, west. So if my boat is going due east, that means what's its direction? What's its direction? Its direction is 0, and so it's got no vertical component. So if I let my boat B, the velocity of my boat B is going to be purely in the positive direction. It's the magnitude of however fast it's going, comma, 0. Because cosine of 0 is 1, so the magnitude of b times 1 is the magnitude of b. Sine of 0 is 0, so the magnitude of b times 0 is just 0. So there's my boat going due east. But there is a current, water, going southwest. So southwest would be 45-degree angle here. So if we let that be my current C. Now again, I don't know how fast my current is going, but I do know if this is 45 degrees here, then whatever my magnitude is, I'm negative root 2 and negative root 2. So my C, it's the magnitude, however fast it's going, times the components of negative the square root of 2 over 2, comma negative the square root of 2 over 2. So I could, in fact, think about this current velocity vector as negative the square root of 2 times the magnitude of C, all over 2, comma, negative 2 times the magnitude of C, all over 2. So, having not been told the speed of the boat or the speed of the current, I can already write their component forms because I know their directions and they're nice directions. So, after 3 hours, the boat has traveled 40 miles. So that's a resultant vector. So the boat is going this way, but the current's pushing it back, right, as the boat is traveling. So essentially, we can think of 3 hours almost like, so here's my boat. It's wanting to go this way. 1, 2, 3, pretend that's nice and straight. But then my current has 1, 2, 3, right? Also, every hour it moves, every hour it moves, every hour it moves. So the resultant vector means what? It has traveled 40 miles and is on a bearing of 110 degrees. So if the bearing from true north is 110, if all of that is 110 degrees, what does that mean its direction angle is? 110 minus 90 is, right, 20. So its direction angle is negative 20 degrees. So what we actually know is my resultant vector is 40 times cosine of negative 20 degrees. That's its horizontal component, comma, 40 times sine of negative 20 degrees. That's its vertical component. But I also know that R is going to equal, well, 3 times B plus 3 times C. We see it 1, 2, 3, 1, 2, 3. That's my R. So what does that mean specifically? That means R is also equal to, well, 3 times B is just 3 times the magnitude of B. 3 times the magnitude of B in the horizontal component, plus 3 times C, plus 3 times, well, this is going to be negative the square root of 2 times the magnitude of C, all divided by 2. So that's in the horizontal, that's my horizontal component. So this must equal this. And more helpfully, my vertical component, I got 0 coming from there, plus 3 times, again, negative the square root of 2 times the magnitude of C, all over 2. Now that is actually incredibly helpful because what can I do? I can actually set, well, I wanted to change colors, but I can set this piece equal to this piece and solve for the magnitude of C. Right, so what I can say is that 40 times sine of negative 20 degrees must be equal to negative 3 root 2 over 2, 3 root 2 over 2 times the magnitude of C. So solving this for the magnitude of C, what is the rate of the current exactly? Again, I multiply by 2, I divide by negative 3 over root 2. Sine of negative 20 degrees. Sine's an odd function, so really this is negative sine of 20 degrees. So if I wanted to, I could just essentially pull that negative out and ignore all the negatives. But I'll leave this in and this in just so we're clear. So if I multiply both sides by 2, that's going to give me 80 times sine of negative 20 degrees, all divided by negative 3 square root of 2. And that, when you punch that into your calculator, is going to give you approximately 6.5 miles per hour. 6.5 miles per hour. So that is the speed of the current. Armed with that, I can now set these two things equal and solve. So if I know that 40 times cosine of negative 20 degrees, which again, cosine of negative 20 is just cosine of 20 degrees, because cosine's an even function. If I set that equal to 3 times the magnitude of B plus, or I'm going to say minus 3 root 2 over 2 times the magnitude of C, which, what do we know the magnitude of C is? We know the magnitude of C is exactly this. So actually, I'm just going to go ahead and erase this magnitude of C and put exactly in its place, because you'll see this will divide out very nicely. 80 times sine of negative 20 degrees, all divided by negative 3 times the square root of 2. What can I say? Well, that, minus, that's going to become a plus. Half of 80 is 40. And so what do I have? If I subtract this now over here, I can say that this will lead me to saying that 40 times cosine of negative 20 degrees minus, because that became a plus, I'm going to subtract 40 sine of negative 20 from both sides, minus 40 sine of negative 20 degrees should equal just 3 times the magnitude of B. And so dividing everything by B, the magnitude of the boat, how fast are the engines working on that boat, divided by 3, I'm going to get 40 times cosine of negative 20 degrees minus sine of negative 20 degrees, all divided by 3, which, since 40 and 3 are not divisible nicely, we're just going to leave it like that. And punching that into my calculator, that's going to give me approximately 17.1 miles per hour. So while the boat essentially travels, well, 40/3 miles per hour in this direction, resultantly, right, which 40 divided by 3 is 1, so 10, anyway. 40 divided by 3 goes in once, right? 3 goes into 10, 3, 9, 13 and a third, right? The engines, instead of moving 13 and a third miles per hour, the engines are moving faster because this current is pushing it back. So that's the speed of the boat if there was no current with the engines. Cool? Alrighty. So last little bit for these notes are, we're going to look again at parametric equations of a line segment. So we already covered this in 6.3 because we did 6.3 first, but we're going to look at this now with a direction vector perspective. So we can use vectors to define points on a line, right? So look over here. R is an arbitrary point, x, y, and it's on the line between the points P and Q. So if I let P be x1, y1, and Q be x2, y2, then I can say from the origin, I can draw directed line segment vectors, right? And so, if R is on the line created between the points PQ, then the vector PQ, right, is in the same direction as the vector PR. What do we know about vectors that are in the exact same direction? Well, they're scalar multiples of each other. So PR is some bigger version of PQ, right? So PR, right, is in fact some T, right? Then there exists some scalar T, so that T times PQ is PR, right? And thus, if that's true, right, PR, T times PQ, what does that mean? We can use that because we can also, from the origin to P and the origin to R, we can do some vector addition here. I can say that from O to P plus P to R, that's equal to O to R. So again, O to R, O to R is PR, well, I would say OP first plus PR. Here it's written the other way. But what is PR? PR is T times PQ. Why on earth is that helpful? Because if we substitute this into component form, then we can look at, right, since OR is our arbitrary XY, and PQ, right, from P to Q, that's going to be tail minus the head, so X2 minus X1, Y2 minus Y1, plus OP is X1, Y1, right? When I distribute the T through, right, and add in component form, this means arbitrary X must equal my initial point plus T times X2 minus X1. And arbitrary Y must equal my initial Y value plus T times Y2 minus Y1. These should look very familiar. They are just like what we did in 6.3. So this gives the parametric form of a line through 2 points. If we want the line segment starting at X1, Y1 and ending at Y2, X2, Y2, then we restrict the domain of the T values from 0 to 1. And you can easily extend this to write parametric equations of a line in 3 dimensions. And when we get to Chapter 8, Section 6, which is coming soon, we will look at this very thing, right? So just to practice once more, write the parametric equations of the line passing through 5, 4 and 2, 7. So go ahead and pause the video, try this on your own right now, pause. Okay, assuming that you've paused, again, I don't use vectors. I'm not going to recreate what we did up there. I'm just going to use the fact that I know, hey, X of T. If I say I start here, that's going to be my initial, so it's going to be 5. And Y of T is going to start at 4. And then 1 second later, I want to be here. So 5 minus 3T will get me to 2 when T is 1. If T is 1, right, and 4, how do I get to 7? That'd be plus 3T when T is 1. 4 plus 3 is 7. Essentially, what did I do? I did 2 minus 5 is a negative 3, and 7 minus 4 is a positive 3. And since I want this to be the full line, I'm going to go ahead and say let T be all reals. So on my interval from negative infinity to positive infinity. That is one possible set of parametric equations, right? What if I started here and went there? What if I traveled at a different rate? There's an infinite number of possibilities. That's just one of them, all right? And thus ends our 6.1 class notes.